Hi, this is Sai Potana, founder at Embedded Systems AI LLC. In this video, we're going to go over the RISC-V RERI specification. That's the RAS Error Record Register Interface. RAS stands for Reliability, Availability, and Serviceability. RERI is the standardized way that RISC-V systems detect hardware errors, log them, and hand them off to software for recovery. This specification became the common language that CPUs, caches, memory controllers, interconnects, and accelerators all use to talk about errors on a RISC-V platform. The life of an error, from silicon to software, is shown in 4 stages. On the far left, the error sources: a CPU pipeline, a cache with ECC, main memory, the interconnect fabric, a PCIe or CXL link, and an accelerator. These are the components doing the actual error detection through ECC, parity, protocol checks, voltage sensors, and so on. When one of them detects an error, it doesn't just raise an interrupt and hope for the best. Instead, it writes a structured record into a RERI error record bank. The second stage. The bank captures what happened, where it happened, and how severe it is. It can optionally raise an interrupt to wake up the next stage. The next stage is the RAS agent, typically firmware, the RISC-V SBI, or a baseboard management controller. The RAS agent discovers which banks exist, reads the new records, and translates them into a standard OS-facing format like CPER, the common platform error record format used for the industry. Finally, system software, the OS or hypervisor, consumes the record, diagnoses, attempts recovery, mitigates, or logs for telemetry. And notice the dash feedback arrow at the bottom. Telemetry can flow back to influence how hardware reports future errors. That's the whole story in one picture. The rest of the sections zoom into each piece. Producers on the left, CPU, memory, PCIe, feed into the RERI error recording infrastructure in the middle, which is just a set of memory-mapped error record banks, numbered 0 through n. Each bank exposes a small set of common registers: control, status, and the record entries themselves, and a notify or interrupt mechanism. Consumers on the right, firmware, SBI, the OS RAS framework, logging and telemetry stacks, read those registers. The single most important aspect is shown at the bottom. Memory mapped register interface. RARI isn't a new bus. It isn't a new instruction. It isn't a new exception class. It's just registers at well-known offsets in physical address space. That's what makes it portable across every kind of RISC-V system, from embedded microcontrollers to server SoCs. An error record is depicted by a data model. The spec defines a 64-byte record with these key fields: a header with version and layout, a timestamp of when the error occurred, an error severity classification, an error type or error code, an error source identifier, so you know which component reported it, a physical or virtual address when applicable, an access type field, that's the ATID, telling you whether the address is a supervisor physical address or a guest physical address or a virtual address, plus context information like privilege levels and heart ID, and finally, any additional component-specific data. On the right, you see the severity levels. The spec defines 4 classes. Correctable. The hardware fixed it. The system keeps running. But it's worth logging because correctable errors are excellent predictors of future uncorrectable ones. Recoverable. Uncorrected, but the OS can do something about it. Fatal, also called UEC. Uncorrected, error critical, needs immediate handling, may halt or reset. And deferred, UED, meaning the data is poisoned, marked corrupt, and handling is postponed until somebody actually tries to consume it. That deferred class is one of the RERI's elegant ideas. Don't panic when you find bad data. Just tag it and only escalate it if it's actually read. Each component can have multiple banks. Each bank starts with a header. Identify tells you about the vendor and their capabilities. Control enables and configures. Status reports flags and counters. And then record. 0 through record N are the individual error entries, and notify configures the interrupt or doorbell. The features listed on the right are what makes RERI flexible. Multiple banks per component, configurable size, overflow handling, because corrected errors can come in fast. Interrupts can happen on new error. Atomic record writes are facilitated so that software always reads a consistent snapshot. And secure access control is provided so that untrusted software can't tamper with error state. Everything again accessed via memory mapped registers. Here, timeline of a single error from the software side is shown. Hardware detects and logs, writes a record into the RERI bank. The RAS agent, firmware or SBI, discovers banks, reads new records, formats them to the OS standard like CPER, and manages and clears them. The OS or hypervisor, the RAS framework, receives and parses, logs and reports, notifies user or admin, and triggers recovery. Then management and telemetry, often a BMC or out-of-band controller, stores, exports, analyzes trends, and enables predictive maintenance. CPU cores, caches, memory controllers, interconnect, and coherent fabric, I/O like PCIe and CXL, and accelerator IP blocks all sit on the top of the same RERI error recording infrastructure, which feeds a shared RAS framework in firmware and the OS. The same interface, the same record format, the same software stack. Whether the error is a single bit cache flip or a fatal protocol violation on a CXL link, the discovery and reporting path is identical. The spec includes a built-in error injection mechanism. You write to a control register with a delay value, and when the counter expires, hardware marks a record valid and races the configured signal, exactly as if a real error occurred. It can be used for ECC injection protocol or parity faults, cache or TLB errors, I/O errors, custom IP errors. This lets teams validate the entire RAS pipeline: hardware detection, firmware translation, OS handling, error recovery, without waiting for a cosmic ray. It's the difference between the RAS code that's been tested in a lab and the RAS code that only runs in production. Here, an example error record is shown. Here, an example deployment in a server SoC is shown. An 8-core CPU cluster, last level cache controller, DDR5 memory controller, and the I/O complex each have their own RERI agent and interface, feeding a shared RERI infrastructure with multiple banks. Firmware, the SBI or BMC, reads them and surfaces a unified view to Linux RAS. With RERI, you have a distributed capture with centralized visibility. Benefits of this spec is summarized here. A standardized record format, a memory-mapped platform-neutral interface, low overhead hardware logging, scalable to many banks and sources, working with both firmware and the OS, supporting service class systems, improving reliability, availability, and serviceability measurably, and enabling predictive maintenance through telemetry analytics. Typical users of this spec are OS RAS frameworks, hypervisors, cloud and data center operators, BMC and out of management, debug and validation teams.